Hello everyone. Now our group 2 section 5 will present the fluid mechanics 1 project. Our title is a comparative study of flow pattern in sudden reductions. In our group, we have 4 members, which is Leong Darwin, me Fujunwei, Muhammad Firhan, and Siti Aisha.
Hello, Assalamualaikum. My name is Muhammad Fidan Hakim bin Fazli. My metric number is CD23004. Today, I want to present about a comparative study of flow pattern in sudden reduction. Introduction. This study explores flow behavior in pipelines, focusing on the effect of sudden diameter reduction on velocity, pressure, and turbulence. While Bernoulli theorem predicts increased velocity and decreased static pressure in such scenarios under ideal conditions. Real-world factors like viscosity, turbulence, and energy losses often cause deviation. Experimental analysis of water flow in pipeline reveal unexpected pressure increase at specific point, influenced by frictional loss, flow separation, and turbulence. By comparing theoretical prediction with experimental data, the study aims to enhance the understanding of flow dynamics in the real-world system, contributing to improved pipeline design and optimization across various industries. Okay, next, for part theory, we have two theories. First, theory on Bernoulli's equation. Second, theory of flow pattern. For theory Bernoulli equation, Bernoulli's equation is a fundamental principle in fluid dynamics derived from the conservation of energy. It relates the pressure, velocity, and height elevation of a fluid in steady, incompressible, and non-viscous flow. The equation is named after the Swiss mathematician and physicist Daniel Bernoulli, who published it in his book Hydrodynamica in 1738. For theory of flow pattern, when a fluid flows through a pipe and encounters a sudden reduction in diameters, its flow pattern changes significantly. This phenomenon is commonly observed in fluid mechanics and has important implications for pressure, velocity, and energy loss in the system. The behavior of the fluid during such a transition is governed by principle of conservation of mass, energy, and momentum.
So now I will continue with the equipments and procedure parts. We total have seven equipments we will use in our experiment. For the first one is the plastic bottle, uh, serve as the water reservoir. Second is the pipes, is connect to the bottle to allow the water flow. Third is the plastic bottle, which is the capacity is 215 meter milliliter for accurately correcting and measure the water. Four is the stopwatch to record the time taken for water to fill 215 milliliter, and the rulers is to measure the internal diameter of the pipes. For the sealant is to schedule and prevent leakage at the pipe water connections, and the last is the water us as the working fruit. So the procedure for the procedure in this assignment is, for the first one is we attach the pipe securely to the outlets of the bottle and to ensure they are not leaked at the connections using sealants. Second, we press the plastic bottle which is capacity 250 millimeter at the ends of the pipes to collect the water. Third, we have the stopwatch ready to ensure the time taken for the water to fill the plastic bottle with capacity 250 milliliter. Four, we fill the bottle with water, and we will start the stopwatch as soon as water begins to flow into the measure cylinder. So after that, we stopwatch when the water level in the measuring cylinder reach 250 milliliters, and furthermore, we record the time taken and repeat the experiment at least 3 times to ensure the consistent of the result. Lastly, we record the times, flow rates, and calculate the velocities and pressure in a table.
Now I present the data collection parts. First of all, we will measure the diameter on point A, which is 0.02 meters, and the diameter on point B is 0.005 meters. This uses of the diameter is to calculate out the cross-section area for input and output the liquid. Next, we will conduct the experiment to get the time taken on fully fill the 550 ml the water bottle. And the first result we get is 11.03 seconds, and the second result is 11.33 seconds, and the third result we get is 11.57 seconds. And the average time taken is 11.31 seconds. Therefore, we can use these data to calculate out the water flow rate, which is 22.1043 ml per second and is equal to 0.000221043 meter cube per second. Now I will present the calculation and the result part. As we can note that the continuity equation is stated the input volume flow rate is equal to the output volume flow rate. And the volume flow rate Q is equal to the BDA, which is the velocity times the cross-section areas. Therefore, we can calculate the velocity of the fluid on point A is 0.0704 meter per second, and the velocity of the water on point B is 1.1258 meter per second. After we calculate the velocity, we can using the binary equation to calculate out the pressures. And since we have using the formula to calculate out the pressure difference, which is 631.23 pascals, then we can know that the pressure on point A is higher than the point B. And the water velocity is on point A is lower than the point B.
For our discussion, the first is we discuss on how to get the velocity to calculate the velocity of water. So the volume of water we will get it by calculating the volume, the ml over s, and convert to m cube over s. We measure the flow rate Q, and it can be calculated as Q equal volume times time, which is equal to 250 ml over 11.31 second is equal to 22.10 ml over s. And for this calculation, we convert with times 10 power of negative 6. Then we get 0.0002210 m cube over s. This is how we get the calculation. Next, in our second discussion, is about the difference on pressure rate or volume velocity flow pattern between the large diameter and small diameter. We can see in large diameter on pressure, the pressure stays higher because the fluid moves slower and has less friction. And in red volume, to retain the same Q, the velocity must be lower because the cross-sectional area is larger. And in velocity, the flow spreads over a greater cross-sectional area, resulting in a lower velocity. And the last one is for pattern. Since the velocity is lower and the Reynolds numbers is smaller, the flow is more likely to be laminar, particularly at lower flow rates. And You can see the difference when in small diameter. The pressure drops faster because the fluid moves faster and experiences more friction. This is for pressure. And for rate of volume, the velocity must be higher to retain the same Q, since the cross-sectional area is less. And in velocity, the flow is restricted to a smaller cross-sectional area, which results in a faster velocity. And then in flow patterns, the last one, for the same flow rate, smaller pipes make the fluid flow faster, which increases the chance of turbulence because the Reynolds number rises. For our third discussion, is about the application in real world, which is in residential firefighting, fire nozzles play a crucial role in controlling house fires and minimizing damage to surrounding areas. Firefighters often use a fog nozzle to cool down the structure and create a protective barrier around nearby buildings, preventing the fire from spreading. At the same time, they may switch to a straight stream nozzle to directly target and suppress the flames at the source. This combination allows firefighters to efficiently manage both the immediate fire and the risk of it spreading to neighboring properties, ensuring a more controlled and effective response. Next, in our conclusion is this study examined how sudden changes in pipe size affect fluid flow, focusing on speed, pressure, and turbulence. It found that fluid moves faster and becomes more turbulent in narrower pipes, aligning with principles like the continuity and Bernoulli's equations. These findings are useful in real-world applications like firefighting, where managed water flow and pressure is essential for safety and efficiency. That's all for our group. Thank you.